We also have to register all our data geographically and in time, because if we don't know where we collect them and how they correlate to each other, they're not going to be a lot of use. At the end, they're transferred to our control and visualization center for further analysis. Now, what are the things we're actually looking at? It's a little sketch of some defects that one can encounter. On the pavement side, again, we may have some tracking, cracks, potholes. We may have the debonding of the pavement at the ceiling layer. Below in the concrete, we may have rebar that is corroded. We also call that, refer to that as delamination. So the radar is supposed to look at the rebar location, the delamination, and the thickness of these pavement layers. The acoustic is focusing on finding these voids and debonding areas. The millimeter wave sensor that we have on our system will look at mainly liquids that are on the surface and also surface properties, dielectric properties. Optical system will give us essentially the topography of the road. We're doing surface and subsurface sensing. The acoustic system uses the tire as the source. We have a whole bunch of microphones, and so this is a non-contact method to assess surface and subsurface conditions of the pavement. The second method is a ground penetrating radar-based system that we call GEARS. This is kind of a two-part system. Because it is a high-risk system, we were aiming for collecting the radar data in a single shot. And if you think about how to sample 2 gigahertz signals in radar system, it's usually done in equivalent time sampling. I'm not going into further detail, but there's a huge speed improvement and shift in the way these systems operate if you could do single shot sampling. So we're going to try to demonstrate that. But at the same time, we're going to need a system that is operational in the field. So in parallel, we customize and assemble a new GPR array system that will be faster, smaller, and less expensive than the ones that you see currently on the market. The millimeter wave sensor is in its development stage. We started with a connectorized version. Right now, we're building our own circuit board, and we're doing some lab testing already. And we can distinguish between materials. And I'm leaving some of those things out because I know I need to get to the end. We have an optical system that will project a pattern on the surface, a known pattern, and based on the distortions that are recorded by the video camera, we will be figuring out the topography of the road surface, hopefully with resolutions of about 5 millimeters, and we can extract from that certainly also pothole cracking and a lot of the surface features. The data will be collected in a data center that will allow different stakeholders to have access to it. There will be a public level, there will be a decision maker level, there will be an expert level or researcher level that takes the raw data, combines it, analyzes it, and puts the resulting layers back into the system. All right, this is my last slide, and I want to leave this up so that Ken can comment on that. This is why we wrote the proposal, and this is why we think that borders is a good idea, and that this could really change, potentially, how road and bridge deck condition assessment has been done. So the area of coverage suddenly increases from isolated, targeted locations that are called out on special vehicles. You can get theoretically all roads. You can cover a whole city, a whole town over time. And it will integrate subsurface information, which means you can try to do preventive maintenance. The continuum of the data collection over time will allow you to really do some monitoring, actually learn about the life cycles of your infrastructure. Because you probably, right now the measurements may be years apart, but you may suddenly have a data set at a certain road you drive by every month, and you can really see how the deterioration process goes about. It will work totally in traffic. There will be no traffic delays, and it will hopefully improve the decision making on what to repair, how to distribute the available resources, and lead more to a proactive management that will save resources.
As the Realist, my business is adapting sensor technology for high-speed scanning of pavements and bridge decks, and then applying those adaptations as a service to the highway agency. So what Ralf here has presented is something that's going to totally revolutionize the type of work that I do. So my interest as a realist is one of adaptation. What is the likelihood that this kind of technology would be adapted, and how? Or to put it another way, if we build it, will they come? And one way to address this question is to go and see what the evolution of sensing technology has been in the highway transportation infrastructure, and then see how this might emerge as the next logical step. The early methods, or the traditional methods that Ralf talked about, tended to be local, and they were applied. The application was triggered by the perception of a problem. We may have a problem here. Let's go run some tests, and the information was, the answers were: is there a problem? Yes, no. What is the nature of the problem, and what do we need to do to address it? So that's kind of the traditional approach to inspection. In the late 50s and moving on for about 15 years thereafter, the major investment in transportation infrastructure capped by the interstate highway system kind of changed the picture significantly and added a lot more dimensions. Many of the facilities that were built during the interstate program have reached their lives or maintenance cycle lives in the late 80s. And so now agencies had networks of thousands of miles of pavements and hundreds of bridge decks, and now they had to make the decisions regarding, on a much larger scale, where are the problems? How should resources be allocated to maximize the performance of the network? And so the technology had to migrate to the more highway speed type of scanning techniques to cover larger amounts of area. Once again, the data collection was triggered by events. The event might be a budget cycle. The event might be a particular corridor needed investigating. For example, we're paving 10 miles of Interstate 93, and you've got 20 bridge decks on the way. What do we do with them? We need to find out. So that would trigger this kind of event. The voter system that Ralf talked about is an entirely different paradigm. There's no trigger. Data is always there. It's going to be continuously collected and will be available at all the time. The question is, how will the agencies respond to this information? Or will they respond? Okay. It's kind of like designing a new app for an iPhone. Will anybody use it? So there are a couple of issues. The data transcends different departments in the highway agencies: bridge, pavement, maintenance. Will the existing management structures be able to deal with it? Also, there's much greater information content available. As Ralf said, there's temporal variations that we don't have available now, and the possibilities of doing things that we couldn't do before. Just to finish off here, I want to discuss briefly what the business model might be for implementing this. The original thought was that a manufacturer would build this and highway agencies would buy this equipment and run these systems, but given the limited resources that highway agencies have, that's not that likely that they would be able to have that expertise internally. And so the more likely scenario is that private firms would acquire this technology and continually collect data on their own and then sell the data to the agencies, to the contractors, to the engineering firms, to whoever needs it at any particular time. So that would require somewhat of a large upfront investment for whoever took that on, but it could be justified if agency commitments could be made a priori so that there was some payback seen in the future. So anyway, that's my thoughts. Thank you.
Question is, has satellite or aerial data been considered for surface inspection? Good question.
Yeah, that's a very good question. I mean, we have not considered that for our project, and one of the reasons is we're trying to complement the whole range of surface methods that are already out there, mainly with subsurface methods. We want to go below the road surface. And so I cannot tell you how accurate. I mean, if those airborne methods would be accurate enough to give you small crack size, and if you would be able to use it in monitoring, I cannot answer that right
I've delved into that a little bit for earthquake engineering, and I'm not sure the resolution's down to the millimeter yet for what's readily available to the public. Yes, for what's, yeah. I think that's, yes.
So what's the price point at which you could see a private firm entering this, like per vehicle?
Great question.
That's a very good question, and this is actually something we're considering in the development of those sensor systems that I was talking about. Our goal is to start, to make those systems, each of them lower cost than what the systems individually are on the market right now. We're starting out with searching for the lowest cost components to build up a sensor system, because obviously the integration of the systems, they're all going to add up. What the actual price point is going to be is very hard to say, because we're in prototype development stage, and how you reduce the price in a couple of higher quantities. It's very, I don't think I could give you a good estimate, but we're making a deliberate effort to make them significantly cheaper than all the systems that are